Welcome to the local host lab, and today we are looking at system design patterns that we commonly use while building scalable software. So let's see. First, let's understand what are system design patterns. Now, if you have worked on backend systems or microservices or any scalable applications, you have probably heard terms like API gateway, circuit breaker, event driven architecture, saga pattern, CQRS. So, all these are system design patterns. We'll get a deeper understanding of what it is in the upcoming slides. So, you probably have worked on, you have heard these terms, or probably you have worked with these. Just to get familiar with what we are going to discuss in this lecture. So, what are system design patterns? So, they are reusable architectural solution to common problems that occur. So, while building scalable or distributed software systems, so there are few common problems that occur, and there are already architectural solutions available which we can reuse. Design patterns are nothing but reusable solutions. So, while building a software, you will come across certain design problems which has already been solved by someone before us. So, it becomes easier for us to uh, tackle those problems. Uh, so they are used to solve recurring engineering problems. So these solutions, they are already proven approaches. Okay, so we already have the design template that we can follow for a certain problem statement, and they are already tested solutions in real world. So we know, so it is guaranteed that the solution will help us solve our problem statement. So why do we need system design patterns? Like why there is a need for it? So obviously, certain problem statements that have certain common problems, they can be easily solved, and also design patterns help us to build loosely coupled systems. Now, while building a software, we want our software to be as loosely coupled as possible. Matlab, there should be as much abstraction as possible so that it becomes very easy to maintain and scale. It helps us to build extensible architecture, which is extensible. You can extend it. Testable applications and production grade software. When I say production grade software, you mean a software which is easy to maintain, easy to scale, and the problem statement that you are going to solve, they are solved in a way using approaches which are tested, which we are sure that, which is guaranteed that these solutions are already tested in real world life. So that gives us the confidence, right? Now, system design patterns, they are categorized, divided into three main categories. The first is creational, structural, and behavioral. So what are creational? Like, see, when we are building a software, what we are mostly dealing with, we are mainly dealing with objects. So how see, any software, like take an example of Java, we use object oriented programming languages. Okay, so we are mainly dealing with objects. So whatever system design patterns that we will study, or we will dig deep into, we are mainly concerned with the behavior of objects, how we are creating the objects, and how objects are behaving. So based on these parameters and factors, the design patterns are categorized into three main categories. Creational, so as the name suggests, it is related to object creation. Structural patterns, matlab how the object composition is going to be, or class composition is going. Class is blue is the blueprint, right? And then behavioral patterns, how the objects will communicate with each other. Now under each categories there are a lot of system design patterns. We'll discuss each one of them in detail in future videos. For now, let's focus on these three main categories. So let's first discuss about creational patterns. So as the name suggests, they deal with object creation mechanisms, how the object is going to be created. Now when we are building a software, as a software engineer, our aim is to keep our software as loosely coupled as possible. We should avoid any sort of hard coding, any sort of tight coupling. Now for Java we are using Spring Boot. Here we have dependency injection, okay, to avoid tight coupling. We want our software to be as loosely coupled as possible so that it is more scalable. We don't want to use concrete implementation, we want to use interfaces, right? So that it is more loosely coupled. And why are we putting this extra effort? So that to improve flexibility of our software, scalability, right? So instead of creating objects directly, there are few patterns that we can use which will provide a better way for creating the objects. We'll discuss about the problem statement, and then we'll in future lectures, and then we'll see how those problem statements are being solved. So why do we need creational patterns? Direct object creation can lead to hard-coded dependencies, rigid architecture. Now whenever there is hard coding, it affects the scalability, which we don't want. Hence we want to keep our software as loosely coupled as possible. So with creational patterns we can achieve something called a centralized object creation. So this will also help us improve abstraction, and also this supports dependency injection. Now these are the types of creational patterns. Creational pattern: singleton, factory, abstract, factory builder, and prototype. So we'll see each single one of these patterns in detail in future videos. For now, let's just stick on the major categories of system design patterns. I hope this is clear. Then the next is structural pattern. So this pattern majorly focuses on organizing classes and objects, and also classes and objects, they communicate with each other, they have like relationships. So these patterns mainly define how these components are connected together, and this also improves flexibility. So why do we need structural patterns? As our applications grow now, so integrations increases, so the external systems differ, and also the relationship between the object, they become more complex as our applications grow. We introduce loads of new features, so that adds more complexity to the overall software. So using these structural patterns, it becomes easier to simplify our system architecture. See, as software engineers, we are not only concerned with how we are integrating new features, but we also want to ensure that our system is flexible, scalable and maintainable. That is something that we want to achieve also while we are integrating new features. So let's see what are different types of structural patterns. So adapter, decorator, proxy, facade, composite and flyweight. There are more, but let's focus on the major, most commonly used ones. We'll see each one of them in details in future videos. Then the last category is behavioral patterns. So behavioral pattern, it majorly focuses on how objects communicate and how the responsibility is distributed, mainly how the objects are interacting or communicating. And why do we need? Because in large systems, the object communication is going to become very complex. The dependency increase, the business workflow, it becomes more complex over time and difficult to manage. So these interactions and communication between objects, these can be cleanly organized using behavioral patterns. So what are the types of behavioral patterns? Strategy, this is one of the most important pattern, and personally I love the kind of work that I do in my organization, the kind of features that I work on, I use strategy pattern a lot. Okay, and we will discuss this in detail. So for now, let's just get familiar with system design patterns and the categories of design patterns. Then the next is memento, observer, template method, command, iterator and state pattern. Now what are the takeaway and final note? So see, just because there are so many patterns, you should not force yourself to use these patterns everywhere. Ensure that if you are using any system design pattern, it should solve any real problems. You are not, it is not compulsory to use these system design patterns. They do help, but it should also result in a positive outcome. You just can't force just because there is a solution. That doesn't mean you should anyhow use it. Yeah, if it makes sense, if it helps you with your problem statement, that you should definitely use, but that doesn't mean you should force. You should force yourself to use design patterns everywhere. You should not over engineer it. So you, as a software engineer, you should have this clarity on how to engineer the solution for a certain problem statement, because over engineering creates unnecessarily, it adds complexity unnecessarily. You are increasing the complexity of your system. It will also become a maintenance burden, like it is like an overkill. And it will, see, in a team everybody has, if a lot, so if you're working on a big organization, on a product, on a software, chances are there are a lot of other engineers that you have to collaborate with. Now over engineering makes any business workflow too complex, so it will add burden to on all team members, right? It will also add to debugging difficulties. Debugging will take longer time. So you should not over engineer. And also good engineering means you should use the right pattern at the right time for the right problem. So these are the takeaway and final note, and I hope this overview on system design pattern It's something you learn something new, and in future videos we'll discuss each system design pattern in detail. Till then, thank you for watching.